Okay, we have started selling A. At the end of day 4, I sell 1610. Oops. By introducing a small policy called a small batch size of 20, I have made a huge loss. Forget meeting the demand. I was only able to meet demand, that also not in full, for product A. Product D, I could not do anything. Product F, I sold only 20. This is my final performance. How is it that the plan which worked so well and made me satisfy my demand to the full suddenly fails, and fails so badly that I'll end up making a loss? All that because I used a policy, and the policy tells me that if I have an efficient batch size, I shall make money, or if I have an efficient batch size, I will reduce my costs, and if my costs go down, I am going to make money. But in the end, I landed up losing money. I lost money because I was not able to satisfy the demand. And if the demand was not satisfied, naturally no money came in. A small local efficiency measure called batch size has converted an efficient money-making plant into a loss-making plant. Now, rest everything has remained same. But when we see this in real life on the shop floor, we know there are going to be variations. There is going to be some delay in vendor. There is going to be some rejection. There's going to be this. So do we focus everywhere? No, we don't focus everywhere. Even though I had removed all of that, we were not able to satisfy the demand with only one of our policies in place. So this is an example or a simulation to show that though you think your policies are very nice, they are counterproductive. And the only reason why this company was able to dispatch was that it only focused on the flow. That means it removed the policy of batch size, and hence they were able to meet the demand, which can also be interpreted as, how is it that they were able to have enough capacity to meet the demand? Meeting the demand means having capacity. So by introducing the batch size, we were not able to meet the demand. It could be interpreted as we don't have capacity to meet the demand. Actually, what was happening was the material movement was slow. That means the flow got hindered when we introduced batches. And this flow, hindered flow, forced us to lose our sales. In this example, I tried to put to you that a simple policy of batch size was good enough to impact the throughput of the company. However, the reason why we worked was that we had a detailed plan for the most heavily loaded machine. If you don't have a detailed plan for the most heavily loaded machine, the chances are that you will be paranoid and you will not know where and why you have lost the production. So first thing, local optimas or batch size issues damage throughput. Second, you need to understand which of your resource is going to limit the flow or is going to be the most heavily loaded resource, and you just need to have a plan for that resource. The most expensive resource may not be that resource. The most sophisticated resource may not be that resource, or a resource which has got a very high changeover time, as we see here, may not be the resource which actually forces you to lose throughput. In this example, blue is the resource which gets most heavily loaded, and if you have a very nice plan for blue, you're going to succeed. If you realize that I have to save setup on green and make sure that I have a plan for green, you are again going to lose throughput, because actually green is not the limiting resource. Green has got enough capacity. Even a big error on green, that means a big planning error on green, is still no problems. But a small planning error on blue, the most heavily loaded resource, can cause you a huge throughput loss.
But let us look at it from the operations point of view, shop floor management. It seems that it is the brown resource which is used one after the another. That means there's a material coming back for operation on the brown resource. Now, since one resource is used for two operations and at different stages of operation the same resource is required, this means that there's a feedback loop, or there's a loop in production process. Now this does make manufacturing complicated. And then on top of that, this brown is also a place where assembly takes place. It requires two raw materials to process together. This may be complicated, but if it does not place enough load on brown resource so that it becomes the most constrained, to focus on brown would make our plans ineffective. And the final impact on the result would be still worse. That means if in our operational policies we treat the constraints and the non-constraints in the same way, we are committing the second biggest blunder of operations management. Because the golden rule of production scheduling says that the level of utilization of a non-bottleneck resource is governed by something else in the system. That means it is governed by the utilization of a bottleneck resource. If one starts looking at it, most of the shocks on other aspects of instability result primarily from us putting these two policies in place, which means that first policy says treat all the resource equally. Second, batch size. When these two aspects of manufacturing start interplaying, this then spills over to the next layer, and the next layer is the raw material supplier, the quality issues, the absenteeism issue, the information issue, the data is not accurate issue, we need better IT systems issue, we need better skill force. This is the second layer. However, the impact on throughput by these cannot be more than 10 to 15%. But what we saw, by keeping these issues on the side and keeping them out of the system, and by varying the batch size and the constraint management part, the impact on output was substantial. Not 10-15% deviation from what we could have made. We were making a loss in one situation and we were making a profit in another. It was not loss of profit, it was total swing of profit to loss. This simulation is an expression that ideal situations, even though may not exist, but in this case it existed, we were still not able to meet the demand. So it is nothing to do with the inherent variability in the system. It is mostly to do with the way we implement our manufacturing policies which causes the maximum damage.
Here is an application on time-based approach to managing operations called drum buffer rope. Let us begin. The first step to understanding the core building concept of drum buffer rope. As we know, there is a manufacturing organization, and if somebody knows a manufacturing organization, yes, it looks something like this. Do you remember these people? Yes, they are our gang of people, our system, our firm, and our process for making something. The figures that you see is nothing but an indication of sort of an installed capacity at every stage. So what you see ahead is nothing but a discrete manufacturing process where people or resources or a gang of people have been trained to work on this item, and their skill levels allow them to be valuable at a particular stage of production. So what we do is we take something which is called a raw material and we process, and this processing is from left to right. That means on the extreme left will be the gating operation and on extreme right will be the finishing operation. So our process that makes something moves from left to right. We take raw material and we convert them into finished goods. This is what we do. A job of any manufacturing organization is to convert raw material into finished goods. And we do that very quickly. Right? We take raw material and quickly, of course, convert it into finished goods. But not that quickly. It's not really that quickly, right? Because there are many stages in between which also need to be done before the raw material can be quickly converted into finished goods. And this is what we see on the shop floor. We see there is work in process everywhere. That means a raw material is lying at various stages at my various stages of manufacturing. And this is called WIP. This is what we see when we look at a manufacturing organization. There is a raw material on the extreme left, finished goods on extreme right. In between these two extreme stages, there are stages of transformation, which we call manufacturing stages. And in front of all these manufacturing stages, we have what we call WIP lying in front of them. Now you see it everywhere. Okay, people may say that, oh, we have less WIP, but we see WIP everywhere. And in fact, let's be honest. Okay, we see them everywhere, but this looks better. It is not that low. There's lots of WIP everywhere. The more the WIP, many times we think that we have enough work for people to do. And not only that, many of our workers at these machines also come under adequate motivational pressure to work faster. Now this looks better. But the joke is also there. Oh, we still see people around. That means unless the people are not inundated under work, which is called WIP, they will not work fast enough. So what looks more like a genuine shop floor is this. We have people who are now hidden behind the WIP.